Hello everybody. We talk about how to measure the weight of the sun and also how long it's going to take for each planet like Mars, Jupiter's go around sun. They are all related. So I show you what the basic way to do it. When Earth is going around the sun, distance is r, so there is a gravitational constant times this is sun's weight and distance square. This is gravity equals, if it's a circular motion, there is an acceleration v square minus r. Well, actually you have m is Earth's weight here, but they are cancelled out, so it doesn't come into the equation. So basic equation is this one. This is very useful equation. The distance to the planet times planet speed square equals gravitational constant and sun's weight, and the gravitational constant is 6.67 times 10 to the minus 11 Newton meter square over kilogram square. And gravitational constant is not easy to measure accurately, but there are some instrument invented the heavy weight together and measure this attraction kind of things, and you can do somewhat good job of measuring it. Those value is like it's used to measure other things in the solar system and readjusted because all the parameter is related. For example, gravitational constant and sun's mass is related to the planet orbit and the speed. For example, g on the Earth's surface is actually this is the acceleration 9.8, around 9.8. You using this one, you can measure the falling speed. You throw the stone, the speed is gonna be this equation. This is the rate of speed change. And what is g? G is actually gravitational constant and Earth's mass. Okay, so everything is related. So after make a measurement, you correct the number and use it and verify with other number measured. So there are a bunch of measured numbers and they are related. Like this is a relationship equation. Then you are going to refine those numbers. Okay, so distance to Earth is 94 million miles. Distance to Earth from Sun, it's about 150 million kilometers. Okay, and distance is usually measured by triangulation. For example, this is Earth and Mars here. When Earth rotates, you measure this triangles. Behind Mars there are a lot of stars, and we know which direction the star is. So we know the angle of a star, and this triangulation, if we know this star and this star, then we know this Mars, this triangle determines the distance to the Mars. So, or when Earth go around the Sun, two location we look at like a very far object, say Saturn, and behind the Saturn has a star, and we know again the angle, and from here it's point to the different star. so different angle, so we can tell the distance. So the distance is relatively it can be measured relatively independently from other parameters. So distance to Earth, once we know the distance of Earth, R, then going around the one in 1 year give you the speed, which is 29.9 kilometer per second, about Mach 60. So Sun is flying at the Mach 60. Believe it or not, not Sun, the Earth. Earth is flying around the Sun at the Mach 60. So mass of the Sun is RV square over G. You calculate it's about 2 times 10 to the 30 kilogram. Okay, so I said the distance to Earth 94 million miles. You look up Google, this one said 92.9, so about 93. 93 and 94, there is a slight difference because Earth is not actually complete circle around the Sun. It's slightly ellipsis. It's as one side is a little bit longer than other side, but within the approximation, it's good enough to use this number. So we get Sun's weight. Once we get the Sun's weight, so then what we get is RV square equals GM. So we know this GM is a constant. And suppose how you calculate the 1 year on Mars. Okay, the Mars, its distance is about 1.5 times from the Sun. So if this is Sun, this is the Earth, this distance 1.5 times longer. This is Mars. Okay, so suppose Mars is R. R is times K. Okay, so we can use K for any other planet. So what happened is this is gonna be R VR square equals R K, and we don't know the speed, but the speed 2 pi R over VR is the time it's required. This is Mars 1 year, right? That's what we want to know. And how do you say T? T is 1 year, Mars 1 year. Okay, so if you plug this in, 2 pi R equals T VR, and you put that into this one, it's going to be this equation. Okay, so R is going to be T VR over 2 pi, and you put that in the VR square T VR 2 pi. No, I'm doing wrong here. Let's do this way, much easier way. If R is 4R, so you know what happened, 4R, okay, the time it takes to go around, how much is this in this case k, right? Time it takes to go around, this is actually not time. Here it's I made a mistake. Okay, this is 2 pi r is entire path, the circle divided by speed. Okay, it's gonna give yeah, t. Oh, this is correct. Okay, so the VR, this and r v square is equal. So if r is, hold on, the let's see, this relationship, so it's r k v r square is r v square. So we have a relationship Mars 1 year k equals the Earth's speed. So Mars speed has to be kv. Yeah, that's correct. So if planet has a 4 times larger radius, then the planet is flying at half speed. Okay, so what's happened is you want to know this one, right? So 2 pi r, and the VR is v k. Okay, is a t. This is tr. This is a Mars or any other planet. So any other planet 1 year is going to be k square root of k and t Earth. So you compare with Earth 1 year is simply multiply k and the square root of k. If k is 4, then it's gonna be 4 to t this Earth. So 8 years. This guy takes 8 years. Okay, so planet takes 8 years if the radius is 4 times larger. If radius k is 1.5, this is Mars. So what do we do is 1.5 times square root of 1.5, and TE is 1 year, Earth year. And if we calculate this, let me hit the calculator. Square root, where's square root? 1.5 times 1.5. So 1.837 years. So the Mars is going around at the 1.837 times. Okay, let's look at the Saturn. The Saturn compared with Earth about 10 times bigger, right? The distance is 10 times. So Saturn year is going to be 10. Let's see, 10 times 10, 31 year. So Saturn go around Sun in 31 year. Okay. Neptune is so far away compared with Earth. If Earth is 100 million, it's going to be 27. So Neptune is 27. Okay, so $140 years. Okay, that's why Neptune was very difficult to find. But because it's 140 years to go around, it doesn't move. It's look like the bright. It's not bright. It's a faint dot on the sky. Look like another star, but actually it is moving. And they finally found out it's a planet. Okay, so that's how we use this equation. So we can calculate every planet on the year. Well, from this you can actually measure the distance using triangulations and compare the value and gravity constant and weight of all the planet. If there is some difference in the value, then you make the measurement a little bit more accurate and try to get the accurate numbers. And that's a history of calculating all the planet movement. And also you plug into mathematical model, all the planet is in the ellipsis orbit. So ellipsis orbit, there are two parameters determines how the ellipsis orbit is going. And once you have that parameter, then that's it. It's you can compare the result. Okay, that's all for today. If you think it's interesting, please subscribe and give like. Okay, and wait for the next video.